gonna start these 2 minutes early because today's tutorial is a little bit long today, and I might take the maybe 5 or 10 minutes more than the time. Alright.
Tutorial number 11, radiation between two surfaces. So the most common or the most important factor in radiation between two surfaces is the view factor. Or sometimes we call it shape factor. Right, so that it can be defined as this is used to compute radiation exchange between two surfaces. Or also can be defined as the fraction of radiation leaving a surface or emitted by a surface I and being intercepted or received by surface J. Alright, so this is the basic definition of the view factor or shape factor. Also, it has another definition. It's all about how surface G can see surface I, or how much the radiation emitted by surface I will be received by surface G, and it's going to be all about the view factor. We call it Fij, and is basically a function of the dimensions of the two surfaces I and J, and the distance as well, right? So a very simple schematic, or a very simple example about this. So if we have surface, let's call it I, and another surface here J, and it might be there is another surface here, we call it surface K. So the first thing you have to do when you have more than two surfaces, you have to name them. So let's call this as surface number 1, surface number 2, and surface number 3. And we know that the surface number 1 has the highest temperature, or maybe it's an electrical heater or something like that. So it is gonna emit heat by radiation Q1, and this Q1 is going to be received by here surface number 2 and surface number 3. So this is the most common case when we have one surface emits heat to another surface. For that case, we have a very good, very common equation. AI Fij is equal to Aj Fji. Is the area of surface I multiplied by the view factor from I to J is equal to area of J multiplied by the view factor from J to I. This is very important equation. Another very important equation in case of we have more than 3 surfaces, which is the summation of the view factors is equal to 1 from n to j equal to 1. So basically this is another very important equation. So let's write it here in terms of I and j. I or let's do it on numbers, right? So from surface 1 to surface 2 itself plus f12 plus f13 is equal to all is equal to, alright? And we're gonna recall this equation. We will be recalling this equation very often in our tutorial because it's very important equation, and we're gonna use it for different cases as well. So I have some special cases, but let me write a note for you. Is the note is a view factor. Fij, if that was the width of surface 1, wi, and this is the width of surface 2, wj, small w, and the distance is L. So Fij is function of the width, wi, wj, and also the length. Alright, so very good, right? So some special cases. If Fij is equal to 0, it means that surface J doesn't see anything from surface I, or doesn't receive any radiation from surface I. So it means surface J doesn't see surface I. And also if Fij is equal to 1, it means that all radiation emitted by surface I is received by surface J. So in that case it is like 2 infinite. So the most common application here is 2 infinite parallel plates, and also surface J fully surrounding surface I. So this is the second special case. Another special case when Fii. So what would if that was equal to 0? Fii is the radiation or the view factor from the surface to itself, right? So the view factor from from surface I to itself is going to be equal to 0 in case of flat plate. Because in flat plate, if the flat plate emits some radiation, it is impossible that this radiation return back to the same surface. So Fii in that case is going to be 0. Another case is convex. If our surface is convex, so the convex is something like that, and if the convex emits some heat, and is very impossible, or it is impossible that this heat going to return it back to the surface or something like that. And Fii is not equal to 0 if the surface is convex. If the surface is convex, because here as a convex, if part of this surface emits some heat and is going to be returned back here, and it might be reflected to the same surface, alright? So it might return here or it might return here. So Fii in case of convex, concave, is not equal to 0, right? So another thing that I would like to talk about is the different configurations between two surfaces. So we have too many common configuration. The first common configuration, common configurations. So the common configurations are, the first thing is view factor between aligned surfaces. And this actually, so two aligned surfaces is something like that, and this is I and this is J, and the view factor between Fij can be obtained by equations. I'm gonna show the equations to you from the lecture, or by figure number 8. Alright, so you can see what's easiest for you, and you can do it this way. So I'm gonna open the lecture right now, and okay. Also the good lecture, so so here's the lecture, like here. The most common configuration is here, the view factor for aligned parallel rectangles or surfaces, and with all the dimension given, you can use figure number 8 to get the Fij, the view factor from the emitted surface, the radiative surface I to surface J, x over, you got to use x over L and y over L from the dimensions given to you. If these dimensions are not given to you, so you can use the very simple equation here, this one. Fij, as I told you, is function of the width of surface I, width of surface J, and the distance between both of them. And you can use this equation. I'm gonna write it as the figure number 3, alright, in the lecture, or page number 12. So you can use either this one for parallel plates here, or you can use aligned parallel rectangles or aligned parallel surfaces here. So you can use either of those, alright? So that's for the lecture. I'm gonna make also the tutorial ready, so we can go at any time. Alright, so I'm gonna come back here. So the view factor between aligned surfaces. Do you guys hear me, right? Just I wanna check that everyone. Alright, thank you. So So the second common configuration in the view factor is two parallel disks, right, or coaxial disks. So they call it coaxial disks. So in the coaxial disks, when we have like two disks like that, and that's I and that's J, and they are they have the same center line, right? So that's why we call it coaxial. And for that case, you got to use Fij from the equations or from figure number 10 here. Here's figure number 10. That's number 8. Coaxial birthday. So if you can do it, you can do it by the equations from figure number 9, or the most straightforward and very easy for me, like you can use the dimensions given to you for the two disks when they are coaxial and parallel, and from L over Ri and Rj over L. So you've got to allocate your point at the x-axis and 1 point from the curve, and you got to get the Fij from here. So the third common configuration is basically two perpendicular disks. So for two perpendicular disks, Fij is also can be obtained from the equation or figure number 12 right here. So the perpendicular disks is something like that. And this is I and that's J, and there is radiation between them, so you can use these equations here. These equations from figure 11 or the equations from 12. So here it's a very complex equation, to be honest, so the most straightforward thing is to use the graph. I mean, it's not going to be very accurate, but if you have time, you can use the equation. If you don't have time, you got to use the other thing. Alright, so that's okay for now. And the second thing that I would like to talk about is what we call the heat. So we've talked about the factor, the view factor. What about the heat transferred? So the heat is going to be obviously function of the view factor, because based on that view factor, the heat will be transferred from one surface to the other surface, which is basically depends on, as I told you, on the dimensions and the distance between the two surfaces, and also it depends on the configuration that we are using. So the second thing I would like to talk about is the radiative heat between two surfaces. So the radiative heat between two surfaces can be defined as Q I to J is equal to A I F from I to J sigma Ti to the power 4 minus Tj to the power 4, right? And this is the view factor. This is very important if we have only two surfaces. So that's for only two surfaces. If we have more than two surfaces, so we've got to use this equation. Qi is the Q emitted from surface I, is the summation from n to j equal to 1. Is AI Fij sigma ti to the power 4 minus tj to the power 4. So if we have like more than, like I'm gonna show an example. I'm gonna write an example here. Like if we have a surface I, j, and another surface k. Alright, so I is the emitter, 1, 2, and that's number 3. So we wanted to know Q emitted by I. So Q here 1 is going to be equal to Q from 1 to 2 plus Q from 1 to 3. Alright, so the Q from 1 to 2 is basically A1 F1 2, we factor between 1 and 2, and sigma T1 to the power 4 minus T2 to the power 4 plus A1 as well, F from 1 to 3, that's 3, sigma T1 to the power 4 minus T3 to the power 4, right? And the dilemma here is to get the view factors. That view factor from 1 to 2 is a common configuration, right? So it's a common configuration, or like we can call it common configuration. So F12 can be obtained, but from 1 to 3, this is not a common configuration. So how are we going to get this F from 1 to 3? So we're going to get this F from the, let's recall the equation that I have told you at the beginning is the summation of Fij is equal to 1. So Fii plus Fij plus Fik is equal to 1. Fii is, as I told you, is a flat plate. It's impossible that the radiation emitted by the surface returns back to the same surface, so it's going to be 0. We're going to left with this Fij plus Fik is equal to 1. Or let me write it in 1 and 2 because I write all things here in 1 and 2, so I'm not going to write this in numbers. So this is going to be F11 plus F12 plus F13, and we're going to write this F12 plus F13. Alright, so F12 is a common configuration, we can get this, but this one we're going to get it from this equation, right? So that's why I told you this equation is very important and we will be using it multiple times, right? So that's the radiation resistance. And also the third thing that I would like to talk about is the two surfaces enclosure. It's a special case or the radiation between two surface enclosure. Where one surface is surrounding the other surface, or one surface is receiving all receiving heat from the other surface or surrounding the other surface. So if you have surface I here and surface J, something like that, and surface I has T1, I is 1, J is 2, T1 epsilon 1, and here the epsilon is going to be contributing because epsilon will be representing surface radiative resistance. I will explain it to you right now. T1 epsilon 1 and area 1, and that's T2 A2 epsilon 2, and there is heat coming out, radiative heat coming out here, Q radiation. So Q radiation from 1 to 2 is going to be sigma T1 to the power 4 minus T2 to the power 4, and over the summation of the resistances, we have 3 resistances here. The 1 over 1 minus epsilon 1 over epsilon 1 area, this we call this thing is the surface resistance, or we call it the radiation surface radiative resistance. And this is gonna be added to the view factor, 1 F12 plus 1 minus epsilon 2 over epsilon 2 A2, because this included here because they are in enclosure, and some of the heat is going to be received by surface J, and surface J is going to emit some heat back to here. So the emissivity of each surfaces is going to be one of the resistances to the transfer of heat by radiation, right? And this is a surface radiative resistance of surface 2. Surface number 2 and surface number 1. Alright, and F12 is the view factor between them, right? And this is the case. And also this has too many special cases to get the view factor between F1 and 2. So I'm gonna show it to you here in the lecture. So the special cases on that is here. So if we have very large infinite parallel plates, so we will because they are infinite, so all the heat transferred from surface I is going to be received by surface J. So F12 is going to be equal to 0, and if we substitute F12 to 0 is equal to 1, and if we put F12 is 1 here, and we take the area is common factor because basically they are 2 infinite long parallel plates, so the area is going to be the same. We are going to be left with this equation, right? So this equation is basically a refine of this equation, right? And also another special case is long infinite concentric tube surface. 2 concentric tubes, while the inner surface is the emitter, the outer surface is the receiver. So F12 is equal to 1 because all the heat radiated from surface 1 is going to be received by surface 2. And here is the special case. Also the concentric sphere, and another case, small convex object in large cavity, right? So keep those cases also in your mind. So I will start solving some question right now about the view factor, and if you have any, does anyone have any questions so far? All right. So question number 1. Question number 1. So how many of you guys are? Alright. Yes. Okay, started. Thank you. Question number 1 is: a sphere is mounted inside the cylinder. Sphere mounted inside the cylinder, and So let's draw the cylinder here. So we have a cylinder. And and there is a sphere mounted somewhere in the cylinder at a distance s from the bottom surface. So this distance is s, and the sphere has a diameter of, or a radius of 5 millimeters. So the radius here is 5 millimeters, and the radius of the circle is 15 millimeter, and also the same for here as well. And this is surface number 1. Surface number 2 is the inner surface. Surface number 3 is the bottom surface, and the top surface is surface number 4. And alright, so given to you the radiuses and the required is F11 and F12, F13, F14. Good. So F11, what is F11? Can anyone answer? So basically it's a sphere, and it is like a convex shape. So F11 is 0, yeah, thank you. F11 is 0. And what about F12, F13, F14? So as I like, sorry, I didn't mention that. Given F13 is formula, is an equation 1 minus 1 plus R3 to the power squared or minus 0.5. Alright, and R3 is the radius of the bottom circle over the distance, right? Okay, and both of them are given to you. So from this equation we're gonna get F13. So from here we get F13 is 0.5, 1 minus 1 plus R3 is R small 3, which is it was 15. 15 over the distance. He told you that you use in an initial case distance of 5 millimeter, and in another case S1, S2 is 250 millimeter. Alright, and while the distance L, or the length of the cylinder, is 500 millimeters. Right, so 15 over 5 square over minus 0.5, and this is going to give you F13 is equal to 0.314. Right, which is a reasonable number. But what do you think about F14? So if this was 5 millimeters, so the distance from here to the top surface is around 245 millimeters. What do you think about the view factor from 1 to 4 from the sphere to the top surface? Is it going to be a very large number or a very small number? This is going to be a very, very small number. And we're going to get this because we're going to get this. Alright, so this is going to be the same case as from 1 to 3. So from 1 to 3 is not a common configuration, right? So we don't have a common configuration when heat is transferred from a sphere to or to a disk or something like that. So supposedly he might give you the value directly, or he might give you something like that to be used in the exam, right? So F14 is going to be the same, 0.5, 1 minus 1 plus R4 square all to the power minus 0.5. And R4 in that case is going to be radius 4 over, not S, because S is the distance between the sphere to the lower surface 3. But the distance from the sphere to the top surface here is L, length minus S, the length of the tube over S. Right, so R4 is basically 15 over 500 minus 5 for the first case. Alright, and when we get this value here, F14 is going to be 0.000229, and that's very, very low because, as I told you, the view factor is how surface number 4 can see surface number 1, and surface number 4 actually right now is very far from surface number 1, so it will receive very, very low radiative heat from surface number 1, and that's why F14 is very, very low. Alright, and so when we recall summation of Fij is equal to 1, we can use this F11 plus F12 plus F13 plus F14 is equal to 1. F11 is 0 as it is convex. F12, we don't know F12. F13, we know F13, it was 0.314 from the equation, and this was 0.000229. So from here, F12 is equal to 0.6579, right? And that's the whole thing. You will have to do it all over when changing S. So requirement number 2, do it again at S is equal to 250 millimeters, right, and see the difference. And your answer is going to, like, it has to make sense as compared to this one. Does anyone have any question for this question? Does anyone have any concern here? That was clear. So you have, from here you have to take care if the relation between surface number 1 and surface number whatever has a common configuration. So if it has a common configuration, you have got to use the specified relations or figures. If it doesn't have common configuration, you have to maneuver between this equation and whatever you have from the other view factors. Okay? Yeah, F1, 3 and 4 is the equation itself was given, right? So that was given here. So only F13 was given, right? So this is the relation, the view factor relation between a sphere and a surface based on R3, which is the radius of the disk 3 over the distance between the sphere and the disk. and as long as it will be the same like from 1 to 4, but the distance is different. The distance here is the length of the pipe, the distance between 1 and 4. This is number 4. So the distance between 1 and 3 is different than the distance between 1 and 4. 1 and 3 is S, 1 and 4 is L minus S, right? So we rewrite this equation in terms of F1 to 4 and R4. R4 is R4 over L minus S. Yeah. So we've rewrite the equation F13 to be corresponding to F14, and we substitute R4 as the radius of the disk 4 over the distance between 1 and 4, which is L minus S. That's it. So we rewrite F13 equation F13 to be corresponding to F14. That's it. So from here we got F13 and F14, and that was an uncommon configuration between two surfaces, and from this very important equation we've got F12. That's good? Good. So the other question is question number 3 from the tutorial. Question number 3 is basically a common configuration and an uncommon configuration, both of them in the same. So question number 3. It is basically two desks, two coaxial disks. Alright, so two coaxial disks, like here. While one disk has a radius higher than the other one, or bigger than the other one, and that disk was 0.4 meters and that disk was 0.2 meters. Is the diameter, right? And this is surface number. As I told you, you have to number the surfaces 1 and 2, or IJ, right? So the distance given between the two surfaces was also 0.2 meters, and the problem said that surface number 2 has a temperature of 500 K and required T1, okay, and given to you in the problem that surface number 1 has a heater mounted at the top side of it. So there is a heater here. Alright, and this heater is going to emit heat in that direction, Q1. And the heater power was 15 watt. Alright, and also given to you the surrounding temperature. The surrounding temperature was T surrounding, we name it T3 is 310K. Alright, and so what is T1 in that case? So we have two surfaces here. We have 1, 2, and 3. We will consider 3 as a surface, as I told you from the beginning that radiation should be from the first lecture. Radiation should be from between two surfaces, and surface number 3 is the surrounding. So the Q here is some part of it is going to be going to surface number 2, and part of it is going to surface number 3. And so let's solve it here. So as I told you, Q1 here is going to, some of it is going to be from 1 to 2, and the other part is going from 1 to 3. And this is basically from the equation. Q1 is the summation of Q summation of Q from N to J is equal to Qi J. Okay. Alright, so these Q's is going to be, and we'll refine it, A1, F12, sigma T1 to the power 4 minus T2 to the power 4 plus A1, F13, sigma T1 to the power 4 minus T3 to the power 4. Right. So what is given and what is not given here? We have area Q1 is giving to you 15 watt. So and the area 1, sorry, and the area 1 is pi over 4 d1 square, and it's basically pi over 4 d1. The diameter of surface 1 is 0.2 meter square. Is gonna give you G1, or area 1 is 4.142 multiplied by 10 to the negative 2 meters squared. And we know sigma is 5.67 multiplied by 10 to the negative 8. So from here we have Q, we have the areas, we have sigma, T1 is the thing that we are looking for, and T2 is given, T3 is given. So the only thing that is not given to you, F1 and F12 and F13. Right? So for F12, that's a common configuration, which is coaxial disks. Look, in the solution manual, he used the equations to get this F12, but I am going to use the figure. I will be using the figure. Figure number 10. Right? So the first thing that we have to know is as long as we have a common configuration, so F12 can be obtained. So let's get back to the figure 10. Okay. So in the solution manual, he used these equations. Where is it? Yeah, here. This equation, right? So coaxial parallel disks, and he used this equation. This equation is basically based on the distance, the radiuses of the two surfaces. So this is also very straightforward. You've got to substitute by numbers, and you've got to use these numbers to get Fij. It's very straightforward. I am going to use the figure just to show you how to use the figure, right? So for the figure, we have to in the x-axis we have to calculate L over Ri, right? So x-axis we have to know L over Ri. The L here was the distance between the two surfaces, which is 0.2. Ri is the radius of the diameter was 0.2, so the radius is 0.1. So the x-axis give to you the value 2. So the curve value was Rj over L, so we have to calculate Rj over L. Rj over L. Rj was the radius of the big disk, and the diameter was 0.4, so the radius is 0.2, and the length was 0.2 is 1. So from the x-axis 2 and from the curve 1, so you have to allocate, you're gonna allocate Fij from here. So at x-axis we have this value 2, and from the curve we have 1 for this ratio here. So Fij is going to be between 0.4 and 0.5, and it's a little bit in the middle, I think. A little bit in the middle, so it's going to be 0.45. Fij is going to be 0.45 or 46. So in the solution manual he got 0.46, which is not so far. The equations are more accurate, but maybe he can ask you to use the figure instead of the equation, so you know how to use it for sure, right? So train yourself about how to use the figure or how to use the equations, and both of them will give you very close values. So we have got F12, and that's actually F12, right? So that's 1 and that's 2. Let's write it here. Okay, and also recall that F12, we need F13. So recall that common equation, summation of Fij is equal to 1. So F11 plus F12 plus F13 is 1, and so F11 is 0, F12 was 0.45 plus F13 is equal to 1, so F13 is 0.55. So you use both of those and substitute into this equation. So I'm gonna do it here. Substitute into equation double star. So let's name this equation double star, right? So substitute in double star, and you're gonna find out. All right, let's do another page here. So when we substitute into equation double star, I will write it back here again. Q1 is A1 F12 sigma T1 to the power 4 minus T2 to the power 4 plus A1 F13 sigma T1 to the power 4 minus T3 to the power 4. So let's substitute by the values we've got, and that was 15, area was 4.14 divided by 10 to the negative 2. F12 was 145. Sigma is 5167 multiplied by 10 to the negative 6. T1 equal 8. T1 to the power 4. T2 was 500k. And you're gonna be plus, or show it this way. That's plus. Area is the same. The view factor F13 was 0.55, and sigma is the same. T1 to the power 4 minus T surrounding, which is 310k to the power 4. So from here you've got T1 as that was the value. Value was 400 something. Right. The value 454. So this equation is only function of the temperature T1, and when you solve this equation you're going to find that T1 is 454, and that's temperature of the emitting surface.